Okay, good morning everyone. Welcome to my concept video. And this whole concept video, my concept video topic is Q-symmetric matrix. Before entering into video, let me introduce myself. My name is Bhuneshwar. I am currently pursuing my undergraduate from IRA. I am presently I am pursuing undergrad in CSE. Now in this whole PPT, or in the supposed to call as a whole video, I am going to discuss about the skew symmetric matrix, and I make sure that I will complete each and every pinpoint of this topic, and at last of the video I make sure that you guys completely get understand about this skew symmetric matrix. Okay, we will move to the further slides. Okay, now let us see what we are going to discuss in this whole PPT and the contents that are present in this PPT. The first, we will discuss about what is skew symmetric matrix, and later we will discuss the properties of skew symmetric matrix, and later further we'll discuss topic called theorems related to skew symmetric matrix, and next determinant of skew symmetric matrix, and next we will discuss about the eigenvalues of skew symmetric matrix and trace of skew symmetric matrix, and important notes on skew symmetric matrix. As my PPT is whole based on skew symmetric matrix, I am going to cover each and every pinpoint of the skew symmetric matrix. As you see in my table of content, everything is related to skew symmetric matrix, and this PPT is whole about this skew symmetric matrix. And let's move further. See, what is skew symmetric matrix? Before going to the whole video, first we should know about the basic definition of a skew symmetric matrix. In mathematics, a skew symmetric matrix is defined as the square matrix that is equal to negative of its transpose matrix. For any square matrix A, the transpose matrix is given as A power t. A square matrix A, an asymptotic matrix A, can therefore be represented as A is equal to minus A transpose. A skew matrix finds application in various fields such as in machine learning and statistical analysis. See, we can find this symmetric matrix application in computer related fields like machine learning, as we use skew symmetric matrix as much as possible, like in photo, since what we call as magnetization of photos or pointing of the photos. Let us learn about skew symmetric matrix and their definition, properties, using solved examples in the following section. See, as I said, a skew symmetric matrix is square matrix that is equal to negative of its transpose of matrix. See, skew symmetric matrix is simple, nothing but if a transpose is there, if we do the if matrix is there, so let it be a B, and if we do the transpose, what is meant by transpose? Just interchanging the rows and columns. By interchanging the rows and columns, we'll get the transpose of a matrix. Just if a given matrix is equal to minus of given matrix transpose, then it is supposed to call as a skew symmetric matrix, as the definition indicates that a skew symmetric matrix is but see, this is another important point, that this symmetric and skew symmetric are defined for the matrix only for square matrix. This is an important point. See, a skew symmetric matrix is a square matrix that is equal to negative of its transpose matrix. It is important to know the method to find the transpose of matrix in order to understand a skew symmetric matrix better. Here we have considered a matrix A. The basic representation, let it be as B. Representing a skew symmetric matrix is as follow. If B is equal to minus B whole transpose, then it is known as skew symmetric matrix. See here, the B, let's say B is equal to, first row is 0 2 4, second row is minus 2 0 3, third row is minus 4 minus 3 0. If let's transpose the B matrix, then this row will interchange into the column, the second row will become the second column, as you see. Third row will become the third column, as in given example 0 2 4, or the first row became as the first column 0 2 4, and the second row minus 2 0 3 become the second column for the B transpose, and third row minus 4 minus 3 0 became the third column of the B transpose. Now we got B and B transpose. Let us see, if I take out minus common from the B transpose, then you can observe that B is equal to minus B transpose. It clearly indicates that B is an skew symmetric matrix. See, if we take minus 2 out the common, then upper triangle matrix will be positive and the lower triangle matrix will be negative. Hence it's proven that B is equal to B transpose and the given matrix B is an skew symmetric matrix. In this way we will find whether a given matrix is a skew symmetric matrix or not. Okay, we will move further. Let us now, in this slide we are going to discuss the properties of skew symmetric matrix. The two important conditions for a matrix to be skew symmetric are that it should be a square matrix such that the number of rows and number of columns should be equal. It means that it should be a square matrix. Secondly, the given matrix should be equal to the negative of its transpose. Here the sum of the important properties of a skew symmetric matrix. When two skew symmetric matrices are added, the resultant matrix will be a skew symmetric matrix. See, if A is a skew symmetric matrix and consider B is a skew symmetric matrix, if we add A and B, suppose we got a matrix called C, then definitely the matrix C will be a skew symmetric matrix. This is the first property. Consider two skew symmetric matrices A and B such that A transpose is equal to minus A, B transpose is equal to minus B. Then we have A plus B whole transpose is equal to minus of A plus B. The trace of skew symmetric matrix equals 0. And here we can find another major example. See, in this slide we are going to discuss about some other properties. The trace of skew symmetric matrix equals 0. See, as one of the row as diagonal limits are 0, when we multiply 0 with any number, as it becomes 0, from this theorem we can prove that the trace of skew symmetric matrix equal to 0. No, it's not a det, it's a trace. See, trace means nothing but the diagonal elements of any square matrix. As to be skew symmetric matrix, as A is equal to minus A transpose, the trace should be equal to 0. And while coming to the next property, the real eigenvalues of a real skew symmetric matrix A, lambda equals 0. This means the non-zero eigenvalues of a skew symmetric matrix are non-real. When a scalar or real number is multiplied with a skew symmetric matrix, the resultant matrix will also be skew symmetric matrix. Consider a scalar value k, B is a skew symmetric matrix, then the resultant matrix is also a skew symmetric matrix. Suppose if we multiply a constant k to a matrix B, then kb whole transpose is equal to minus kb. If we multiply even a constant, it won't affect on its skew symmetric properties. From this we can derive this kb whole power transpose is equal to minus kb. Let us see some other properties. For any real skew symmetric matrix A, I plus A will be then invertible where I is an identity matrix. See, if we take an skew symmetric matrix supposed to be in A, then if we add I identity matrix I, then I plus A matrix will be invertible. Invertible is nothing but inverse, where I is an identity matrix. I is an identity matrix. Identity matrix means it's an principal diagonal matrix where all principal diagonal elements are 1 and remaining all other elements are 0. Let us take an example call. Let's take an identity matrix 2 into 2 identity matrices. 1 0 0 1 will be the rows of the 2 into 2 square identity matrix. This will be the one of the property. For any real skew symmetric matrix, A square is a symmetric negative semi-definite matrix. Now in the slides we are going to discuss about theorems related to skew symmetric matrix. There are two important theorems related to skew symmetric matrix. In this session let us learn about these theorems along with their proofs. See, for any square matrix A with real number elements, A plus A transpose is skew symmetric and A minus A transpose is skew symmetric. As this formula we are learning from our previous classes, if we take a matrix A, we can further subdivide it into a sum of, we can express it in sum of skew symmetric matrix and symmetric matrix. From that proof we will prove that any given matrix can be expressed as A minus A transpose is a skew symmetric matrix. Let us see the proof for this one, for this theorem. Let us take P is equal to A plus A transpose. Transpose of P can be given as P transpose is equal to A plus A transpose whole transpose. See, if we take P is equal to A plus A transpose, if we whole transpose the P, then it will become the whole transpose of A plus whole transpose as I had written on the slide. Then we are dividing the whole transpose into a single element, then it will become A transpose plus A transpose whole transpose. As A transpose stands, we know that if A power 1 whole power minus will be A, from that we can conclude that A transpose whole transpose will be A. So A transpose plus A transpose whole transpose is equal to A plus A transpose. As we got the previous, A plus A transpose is equal to P. Then A plus A transpose is a skew symmetric matrix. Now next let us consider Q is equal to A minus A transpose. Q transpose is equal to A plus minus transpose whole transpose. Then minus will be out. We can take out minus. Then A transpose minus A. See, if we take out minus common again from A transpose minus A, then it will become minus A whole A minus A transpose. Then as from when we declared a condition called Q is equal to A minus A transpose, therefore we can conclude that Q is equal to minus Q. From this we can conclude that A minus A transpose is a skew symmetric matrix. Now let us see the second theorem. Any square matrix A can be expressed as sum of symmetric matrix and a skew symmetric matrix. As we've seen first theorem, it is we can call it's a child theorem for the first theorem. Let us take age. Let us first of all let us see, consider age equal to half of A plus A transpose plus half means nothing but 1 by 2, half of A minus A transpose. Here A transpose is a transpose of a square matrix A. As I discussed what is meaning of transpose before, here A power T is nothing but A transpose, where we transpose the A matrix. What we will do, we will interchange the rows and columns there. That's it, nothing else. If A plus A transpose is a symmetric matrix, then half of A into A 1 by 2 into A plus A transpose is symmetric matrix. See, before theorem we came to a conclusion that A plus A transpose is a symmetric matrix. See, if we multiply any constant to a matrix, its property won't be changed. From that point we can conclude that A plus A transpose into 1 by 2 will be a symmetric matrix. And in the before theorem we came to another conclusion that for a given matrix A minus A transpose is skew symmetric matrix. Then if we multiply a constant, its property won't be get changed. So from this point we can conclude that 1 by 2 into A minus A transpose is also a skew symmetric matrix. See, now we will add, let us consider 1 by 2 into A plus A transpose as C and 1 by 2 into A minus A transpose as D. Let us add C plus D. Plus half transpose minus half transpose will be get cancelled. Half of A 1 by 2 A plus 1 by 2 A will become A. This is the proof where we can conclude that any given matrix A it can be expressed as symmetric and skew symmetric, nothing but 1 by 2 into A whole A plus A transpose plus 1 by 2 into A minus A transpose. This whole theorems will be around this point. Any matrix can be represented as symmetric plus skew symmetric. This is one of the main theorem in the whole matrix chapter. Try to concentrate on this point. Now let us see determinant of a skew symmetric matrix. We all aware of determinant matrix. I don't want to discuss about this determinant of matrix anymore. The determinant of a skew symmetric matrix having an order equal to an odd number is equal to 0. So if we see any skew symmetric matrix whose order is 0, whose order is odd, then we can directly write its determinant is equal to 0. Let us verify the property 3 into 3 odd. If you see basically skew symmetric matrix is defined for a square matrix 3 into 3, 2 into 2, 4 into 4. If the order is in the form 3 into 3 or 5 into 5, if the order is odd, then we can directly conclude that its determinant will be 0. If order is 0, there will be another point. Let us see verify how odd into odd will become 0 by B is equal to, let us define one matrix. If we find the cofactors and get the determinant, we'll conclude this point that determinant of odd order skew symmetric matrix will be 0. Therefore we can conclude that the determinant of skew symmetric matrix whose order is odd will be 0. and if you try to find the even for the order of even, it will be a particular value. We can blindly conclude that it will be 0 or 1. See, I did not mention in the PPTs, it does not mean that it values will be, but it will be there, it will, but it's vary according to the matrix. We can't, there won't be any particular value for the even skew symmetric matrix. There will be a value, but for the odd order skew symmetric matrix, the determinant will be 0. Eigenvalues of skew symmetric matrix. We all know about the eigenvalues and eigenvectors. I think as we know, the eigenvalues of a skew symmetric matrix are either 0 or imaginary values. For eigenvalues, there will be only two possible conditions for eigenvalues. Either they will be 0 or imaginary values. There won't be any real values or the integer values for the eigenvalues of a skew symmetric matrix. The real eigenvalues of a real skew symmetric matrix, say lambda equals 0. This means the non-zero eigenvalues of skew symmetric matrix are non-real. Non-real is nothing but imaginary values. Proof for that statement which we discussed earlier. Let A be a square matrix and lambda be a eigenvalues of A, and X be an eigenvector corresponding to the eigenvalue lambda. Let us consider a matrix A be a square matrix and lambda be an eigenvalue of A, and X be the eigenvector corresponding to the eigenvalue lambda, where X is another eigenvector corresponding to the lambda. Lambda means eigenvalue. For every eigenvalue there will be corresponding eigenvalue, right? From this we can take X will be an eigenvector for corresponding value lambda. From this we can say that from characteristic equation Ax is equal to lambda x, where the characteristic equation says that A minus lambda I is equal to 0. From this we can get the equation Ax is equal to lambda x. Multiplying both sides by a bar transpose, A bar is nothing but the conjugate of eigenvector x. We get x bar transpose Ax is equal to lambda x bar transpose x equal to lambda of modulus x whole square. Note that term x transpose is an dot linear product of x bar and Ax. Since the dot product of commutative, we have x bar transpose into A into x is equal to Ax whole transpose x conjugate equal to x transpose A transpose x inverse. Since A is a skew symmetric matrix, we have A transpose is equal to minus A. Substituting this into the above equation, we get x transpose A transpose x bar, x transpose into A transpose into x bar is equal to minus x transpose minus x whole transpose into A into x bar. Taking the conjugate of Ax is equal to lambda x and use the fact that A is a real, we have A x bar equal to lambda bar x bar. This means lambda x whole bar we can take, as lambda will be a constant value. If it's not constant, if suppose it's in imaginary, then we can find if it's in a real. If it's in a real, it won't be any have conjugate. The real number will be constant. Thus we have minus x whole transpose into A into x, as these are real what we call, as these are in the vectors form, we should use the vector product dot product minus x whole transpose into A. We should not use a normal multiplication here. Minus x whole transpose into A x bar is equal to minus x whole transpose lambda bar x bar is equal to minus lambda bar modulus x whole square. From this step we can derive minus lambda bar into modulus of modulus x whole square is equal to lambda of modulus x whole square. Since x is an eigenvector, it is non-zero by definition. Thus modulus x is not equal to 0. Hence we have minus lambda bar is equal to lambda. From this we can conclude that lambda will be 0 or pure imaginary number. See, if we won't get 0 anyway, then the only possible way to get the eigenvalues are imaginary numbers, right? The the imaginary numbers what we will get are purely imaginary. There won't be any what we call, so there won't be any real part. Suppose if you take a real imaginary number x plus iy, purely imaginary is nothing but x term will become a 0. Purely imaginary denotes that there won't be any real part. There will be only imaginary I part in the given imaginary number or complex number, as lambda is 0 or purely imaginary number. Now let us see the trace of a skew symmetric matrix. Trace of a matrix is defined as sum of the diagonal elements as discussed under the properties of skew symmetric matrix. The diagonal elements of a skew symmetric matrix are 0. Therefore the trace of skew symmetric matrix always equals to 0. As in before I discussed that if for skew symmetric matrix, for a matrix should be a skew symmetric matrix, then its values definitely should be equal to 0. For a real matrix, it should, if it's want to be a what we call, for a real numbered matrix, if it's want to satisfy the condition of skew symmetric matrix, its diagonal limit should be 0, as I discussed earlier, right? So if we add all the zeros, we will definitely get a 0. Some of the zeros will be 0, right? From this we can conclude that trace of a skew symmetric matrix will be 0. Excuse me. Important. Now let us discuss important notes on skew symmetric matrix. Here is a list of few points that should be remembered while studying the skew symmetric matrix. A matrix for which the transposed form of equal to the negatives of the original matrix is called a skew symmetric matrix. Any matrix can be expressed as sum of symmetric and skew symmetric matrix. For a square matrix A is equal to half of A plus A transpose plus half of A minus A transpose. If the order of a skew symmetric matrix is odd, then the determinant is equal to 0. These are the major whole properties which we discussed in the earlier, and this should be remembered for this skew symmetric. So I hope so you will get these points. And this is my whole PPT, and for whole PPT I conclude that you got the main important points of this skew symmetric matrix. From earlier I discussed from the basics, right? Skew symmetric matrix properties and trace and eigenvalues and eigenvectors. I think so I covered the whole in the video about the skew symmetric matrix. Okay, thank you.